Hello everyone, welcome to Azure Service Bus Messaging Deep Dive. My name is Sean Feldman, I'm an Azure advisor and Azure MVP, occasionally blogging and tweeting. Azure Service Bus is an asynchronous messaging cloud platform that enables you to send data between decoupled systems. Let's have a look at the options in Azure in general to understand why Azure Service Bus is such a great asset in your toolbox. What are the messaging options that we have in Azure? Quite a few. Notification hubs, which allows mobile push notifications. Event hubs for telemetry, streaming, ingestion. There's also an IoT hubs for IoT messaging, of course. There's an Azure Relay, which enables hybrid solutions without the need to open a firewall connection or perform any intrusive changes to a network infrastructure. There's a newly event grid introduced recently, which allows event distribution with uniform event consumption based on a publish-subscribe model where messages or events are pushed rather than being pulled. There's also an old but still good storage queues, allowing asynchronous message queuing between applications. And there is Azure Service Bus, which is no more, no less, enterprise messaging. Let's have a look at Azure Service Bus for queuing purposes. In traditional systems, we always have senders and receivers, or message producers and consumers. In this case, a sender is trying to send a message to a receiver. What happens is there's temporal coupling due to the nature of synchronous communication. With asynchronous messaging, this is fundamentally different, as the problem is tackled as any other problem distributed system. Rather than sending directly messages from sender to receiver, a queue is introduced in between. The sender sends the message to the queue, and when the receiver doesn't have to be online, when the receiver comes online, it consumes the messages, and by that does not require the sender to be online. Furthermore, thinking about the communication in an asynchronous manner forces developers to recognize that working with a remote application also slower and encourages design of components in a high cohesion, thinking through how to decouple the components and make by that system a bit more reliable. The two major ASB entities that we're going to talk about are queues and subscriptions, topics with subscriptions. If you can think at this point about subscriptions as queues on steroids, and we'll talk about subscriptions a bit later. But what are the real differences between the two? Well, a message can represent an intent or a fact. An intent has some expectations associated with it. Expectation is for specific action to take place at a certain destination where that message is sent. For example, deposit $100 to account, or make customer a preferred customer. A fact is a declaration of a historical event that took place. It's a broadcast to the world, if you wish, and no expectation is associated with it. We also don't know who's going to receive an event. For example, a customer became preferred. We just announce it. We don't have any expectation because it's already happened in the past, as opposed to an intent message, which instructs something to happen. Another example, the $100 was deposited. Let's have a closer look at the building blocks of Azure Service Bus. First of all, there's a remote service, also known as a broker, represented by backend stores and gateways, which are internal details that we don't really care about that aspect. For now, we'll just call it broker or server side. There are also entities used to store and operate on messages that reside on the broker side. Those are queues, topics, which distribute messages between subscriptions, and subscriptions usually have rules to capture specific messages. All the entities reside within a namespace. To access those entities in order to send and receive messages, a client is required. There is .NET client, there is Java client, there is Node.js client, and there are other clients based on the stack that you're using. For the .NET, there are currently two clients. One is Windows Azure Service Bus, which operates on SBMP, a proprietary protocol, and AMQP 1.0, which is an open protocol. And there is a newer version of the client called Microsoft.Azure.Service Bus, which is .NET Standard compliant and cross-platform, which solely operates on AMQP 1.0 protocol. What about messages? Well, an ASB message, also known as a brokered message, is an envelope containing headers and a body. Headers are always limited to up to 64 kilobytes, and that includes standard headers or system headers, or custom headers or user-provided headers. Message size, well, not as generous as some other queuing systems, such as MSMQ, for example, but it's fairly good. There are two variations, 256 kilobytes for standard tier, and I'll mention tier in a little bit, and up to 1 megabyte for premium tier. Both maximum message sizes include headers. Now, what happens if you need to go beyond these sizes? Well, there is a claim check pattern which you can implement, or for the new client, there is a plugin which does that out of the box. Now, I mentioned tiers. As a matter of fact, there are 3 tiers: basic, standard, and premium. Basic is only allowing queuing, so not that much of benefit over, for example, storage queues. But standard and premium are the ones that offering the bang for the buck. Standard tier is a multi-tenant option where multiple customers share resources. Premium tier is a dedicated offer with predictable and reliable performance, usually achieved through resource allocation in what's called message units. And currently, premium tier offers 1, 2, or 4 messaging units based on your throughput that you require. Premium tiers of recent is billed per minute, which means it's especially great for things like testing and dynamic namespace provisioning when you can tier those down the moment they're not required anymore. While performance on the standard tier is hard to predict due to the noisy neighbor challenge, on the premium tier, we're talking about thousands of messages per second with very consistent behavior. Note, has to happen within data center. Let's talk about sending and receiving messages, which require clients, a client to send and a client to receive. Let's focus on these clients for a little bit. For sending operations, in order to send message, you have to know what type of entity you're sending to. You can send either to queue, using queue client, or topic client, sending to a topic or publishing a message to a topic. Or if you want something that is more frameworky and entity agnostic, you can use message sender, which doesn't differentiate between queue and topic as long as you provide the path. Once the message is sent, it needs to be received. Receiving can be done from a queue using queue client or a subscription using subscription client. And as you already noticed the pattern, there's also a message receiver, which is entity agnostic and can receive from either. Again, quite nice for implementing frameworks. Now, when receiving messages, there are 2 different receive modes. One of them is called receive and delete. A broker has messages. A consumer comes online, in this case consumer A, and retrieves a message. Once a message is retrieved, it's removed from the broker. The message is gone. The second mode is called peak lock, where a consumer requesting the message gets that message, but the original message is not removed from the broker, meaning that the consumer has to acknowledge the receival in order for broker to remove that message. Keep in mind, peak lock is at least once delivered. Receive and delete is at most once delivered. You should use receive and delete mode with caution, and usually when you don't really care if a single message is going to be lost. Some sort of telemetry data, for example, where a single message doesn't really matter. Well, then I would argue if Azure Service Bus is the right mode for you. Or if you need the throughput, because you don't have to go back to the server and every time acknowledge receival of the message. Now keep in mind with peak lock mode that we're talking about consumers that can be multiple, therefore they're competing, and there is a chance to receive and process message multiple times. Now, acknowledging message is not the only settlement operation that can take place. Upon receival, as we said, We can complete a message when it's marked as completed and removed from the queue. It can be abandoned, which means that the message eventually becomes visible on the queue and can be received later. A message can be deferred, not delayed. Means message will remain on the queue and can be received later, but not by just asking for a new message. It requires to specify sequence number of the message, meaning that the consumer of deferred messages has to know those sequence numbers either through the system or by retrieving the message earlier and registering the sequence number in some data store. Last but not the least, message can be dead lettered, and then messages move to dead letter subqueue, which can be processed later to retrieve messages that, for example, failed processing or were poisonous. The last is not exactly settlement, but something to keep in mind. A lock on a message in peak lock mode, when it expires multiple times, defined by maximum delivery count, the message will be moved to the dead letter subqueue automatically. So keep in mind, abandon is not the same as defer. Deferred messages can only be retrieved by their sequence number, and messages can be dead lettered explicitly if needed. So at this point, we really went quickly through Azure Service Bus, and now let's look at some of the features that it offers. And because Azure Service Bus is an enterprise service bus service, we're probably going to scratch the tip of the iceberg and look at some of them, not all. First feature is Message Handler API. Whenever your application has to process messages, it has to receive those as a constant stream, which means you have to implement a message pump. The process is some piece of code that continuously running retrieves the messages and performs the settlement, either completes, abandons, defers, or dead letters those messages. And in order to increase your throughput or ability to process in parallel, concurrently, a pump should be able to process multiple messages per second. This is what Azure Service Bus provides out of the box with what it calls Message Handler API to implement that message pump. The pump is implemented on your behalf via message receiver, where you can register a message handler or a callback. That's your piece of code that will be given every message that is coming in, and you can perform the processing, send out messages, etc. When a callback is registered, also message handler options need to be specified to provide things like concurrency level, for example, how messages you want to process concurrently, or lock auto renewal. What happens if you receive a message and you cannot process it within a certain period of time defined on the entity, which is the maximum time, and you would like the pump automatically renew that time, basically extend the lease on the message. Exception callback, which receives the exception received event arguments, providing details such as when the exception happened, what entity it was, or what's the failed operation name. Was it receiving, confirming that the message was received, or trying to extend the lock or whatnot. Details about the namespace that you were using at the time when the operation has failed. And obviously the failed exception message itself for the general troubleshooting. Next feature is a duplicate detection. So imagine the real world, two documents, duplicates are sent, and you don't want to reprocess the same message twice. What happens, the broker has capability to deduplicate messages if those are duplicates and drop them without even sending to you or attempting to process. Now you have to keep in mind that it's only based on ID, though there are ways to generate ID based on the body, and duplication time period has to be specified per entity, and it won't hurt if idempotency on a consumer is implemented as well, just to make sure that if a duplicate arrives after the fact that time window has expired, you still don't process those duplicates. Next really cool feature is auto forwarding. Auto forwarding allows to send messages automatically or forward messages automatically from one entity to another queue, or topic within a single namespace. Now, this is a guaranteed operation, meaning that it will never fail on the broker. There is also a possibility to chain multiple entities, multiple queues, or multiple topics, but you have to keep in mind that there is a rule of 3. You cannot have more than 3 hops between entities. If that happens, the message will be dead lettered. And again, forwarding is native on the broker, therefore it's guaranteed. I mentioned dead letter queue. Dead lettering is basically expired or undelivered messages that exceeded, for example, maximum delivery count that are placed into a special sub-queue that can, and those messages can be retrieved and inspected later. Unfortunately, there is no centralized dead lettering with Azure Service Bus, but thanks to auto forwarding, it can be easily implemented. The other things to keep in mind, dead lettering happens for a reason, and that reason is always stated in a header called dead letter reason. And forwarded DL-queued messages have a header called dead letter source, which indicates what queue the message originally failed in. A message expiration is a very handy feature, which allows to send a message with a defined time to leave period. And once that TTL period expires and message has not been received, the message is simply dropped and will never be received. This is good for time-sensitive messages. For example, if you send a message that has only meaning for the next 5 minutes, a second after 5 minutes, it's irrelevant, and if it has not been received, there is no point of sending it again. One more thing to mention, messages are cleared when a client connected. That means that all the messages with expired TTL will reside within the queue until there's at least one connection. Something to watch out for because you don't want your queue to overflow if there are no connections. On the other hand, if you're using messaging, you're most likely to have connections. Ephemeral entities, those are entities, queues, topics, and subscriptions created for temporary usage and can be automatically deleted if they idle for longer than some defined period of time. It's quite a helpful feature for self-cleaning or entities that are dynamically created and removed, for example, testing purposes. You have to keep in mind, though, that minimum is 5 minutes. You cannot go lower than that, and any messages contained within those entities will be gone as well. Next topic is scheduling. Not deferring, but scheduling. It's a message that we would like to send in the future, but we have that message right now. We can specify the future visibility time on the message itself, send it to the queue, and once that time arrives, the message will become visible and can be consumed. So basically, this is a really nice feature for scheduling messages in the future, and it can be scheduled up to years, more specifically time span maximum. But keep in mind that doing that is a little bit of a smell because that literally indicates they're using messaging system to be your data store. Next one is batching, a very powerful feature that allows to send to a destination multiple messages. So for example, let's say you process an Excel spreadsheet. As a result of spreadsheet, every line item generates a message, an event, for example, and you want to send them. You can send one by one, which is very inefficient because of the latency involved, or you can package all of the message in a single batch and dispatch it. Now, it's an atomic operation, meaning that all the messages will either succeed or fail. It's only a single destination. You cannot mix messages with different destinations. There is a hard limit of 100 messages or less, and the total size of the batch is limited to the maximum message size on the tier you're using. In other words, total size of the messages cannot exceed 256K or 1 megabyte, depending on what tier you're using. The next option is using transactions or atomic sends. So we have, again, a single destination. Messages are sent to that destination as a part of transaction. So not as a batch, individual messages. Again, the benefit is that we can send one by one, i.e. we don't have to generate all the messages in order to send them as a batch. We can do it one by one. We have a transaction scope which can be completed or aborted as a result of final operations. Again, single destination on the same namespace, same limitation of 100 messages or less, and total size that cannot exceed maximum message size. Now, a really nice feature, and this is where Azure Service Bus shines due to the transactional processing capability, is atomic sense with receive. It's a very common scenario where your logic receives a message, an incoming message, which triggers some outgoing messages. For example, perform calculation, that's an intent, we're sending a command. And I have received this message, or notify everyone, or announce about something that happened. The messages don't have to go to the same destination. They could go to different destinations. What happens is that we can wrap the incoming received message and the outgoing messages in a transactional scope and either commit or roll back. So incoming and outgoing messages will participate in that transaction and will be either successfully delivered and the incoming message will be completed, or everything will be rolled back and the incoming message will be available again. It resembles to a traditional transaction, which you could probably do on premises with DTC, but this is not DTC, and transaction is only applied on the messages, not any other resource, such as database, for example. As I mentioned, outgoing destinations can be multiple, not just a single one. It still has to be single namespace. Azure Service Bus doesn't support multiple namespaces or transactions spanning multiple namespaces. And the nice thing that we get is there's no ghost messages, which are quite common with other messaging services. And there's more to queues than just a queue. First of all, we've mentioned dead letter queue, right, as a sub-queue. Every queue has that one, and subscription being a queue on steroids has as well. There's a transfer queue, which we don't access directly, but it has a dead letter queue as well, meaning that if your transaction is in process and the destination where we send messages is not available, the message will never be lost. Transaction will succeed, but that message that could not reach the destination will be sent to the transfer dead letter queue, which can be processed separately. So what does that mean? Another dead letter queue to monitor to ensure that there are no messages that were missed out. An order of $1 million is quite important, and we should never lose it. And messages are never lost. The next feature is PubSub, which is a very strong feature, selling feature of Azure Service Bus. It allows to decouple between senders, receivers, and send the notifications or broadcast notifications about things that happen. Usually, messages are sent to queue or topic. In order for PubSub to work, it has to be a topic, because topic can contain subscriptions, multiple subscriptions. Each subscription has rules to specify how messages are filtered out. Therefore, there are filters, and there's also action. What happens when a message satisfies the criteria specified in the filter? There are certain actions that can be performed. The actions are performed on the headers. So, for example, a filter like system property label needs to contain the word rush, or a custom property, custom header called amount, needs to be 100 or more. And an example of action would be set a custom header, a custom property called priority to a value high. Here's another subscription which has its own filter and its own action. This one is filtering out all the normal priority messages. The filter is amount has to be less than 100, and the label should not contain the word rush. When subscription receives a message like that, it will stamp the headers with a custom header priority set to normal. So we can broadcast without knowing the recipients, which is a great feature. Message headers can be mutated using actions, and we can enable different levels of processing. We can do much more than that with topics and subscriptions, but in the next session. Now, rules can be not just a single rule, but multiple rules. Rules evaluated using OR logic for a given subscription. For example, subscription MySub will have rule 1 and rule 2. So it's enough to satisfy one of the criteria, either labeled to contain the word rush or amount to be 100 or more. Another feature, which is extremely complicated and extremely powerful, is being able to process messages in order and order guaranteed. It requires utilization of Azure Service Bus message sessions. For example, we have messages coming from 2 sessions, session 1 and session 2, the blue and the green, and we have different consumers. Each consumer can consume a session, and it's guaranteed by Azure Service Bus that it will only receive messages for that given session. So not only we guarantee messages from the same session, but also the order in which those messages were sent. Now, what happens when errors happen? Well, there's an exception handling. Built-in retry policy, which is highly optimized, and the client performs retries on our behalf. And there's also isTransient property on every Azure Service Bus exception, which indicates that an operation should be retried, and if retried, most likely will succeed. And that's it for Azure Service Bus. Thank you so much for joining, and I hope you'll find another great tool under your tool belt, which is Azure Service Bus.